Okay, so in 8.1, our focus is going to be on basic integration techniques. So we're going to be reviewing some stuff that you've done before. In fact, we began the course by looking at some examples, reviewing the substitution method. So we're going to do that pretty briefly. Then I'm going to show you some other methods that we can use for integration. So we're going to really expand on our world of integration techniques in this section and then throughout this chapter. So recall the way substitution works. If we have an integral like, for example, x over 3x squared plus 1 dx, then the way we approach the problem is we look to see if we have, well, if we have a basic integral, we just try to use our power rule or one of our other derivative rules to work it out. But if we happen to have a composite function, one inside of another, then we need to usually use some type of substitution. And if you can't really detect the composite function, like you have something, a quantity squared, quantity inside of a cube root, something inside of a trig function, you have a trig function to a power, any of those things like that, then if you have a single fraction with stuff in the bottom that's not just an x only, then you have a composite function. And we can let u be the denominator. Let u be the denominator. Then we can differentiate implicitly, find out that du requires me to have a 6x to go along with my dx. And so we know that dx is going to need to have a 6x. So we account for our u, and we look to see what else we have. In this case, we have a dx, and we also have a lonely x, which is good because that fits the variable part of what we need here. So that's great. The thing we're missing here is the 6. But that's easy to account for because we can divide by 6 on the outside, and then multiply by 6 on the inside. So that now we have everything we need to carry the substitution process through. Right. We have u accounted for, right, and we have du accounted for. So we're able to carry the substitution steps straight through. 1/6 integral 1 over u du. But we know the integral of 1 over u du is the natural log of the absolute value of u. And remember, with any indefinite integral, we have to have the constant of integration. Okay. And then we can substitute back in. U is equal to 3x squared plus 1. So 1/6 ln absolute value, 3x squared plus 1, plus a constant. And then here we can do one extra thing. Because 3x squared plus 1 is always positive, right? X squared is always going to be positive, 3 is always going to be positive, plus 1 is always going to be positive, then we can actually drop the absolute value here and say this is 1/6 ln of the quantity 3x squared plus 1 plus our constant c. As a second example here, let's consider the integral of cosine of 5x dx. So we recognize the composite function. We recognize the composite function. We have the 5x function inside of the cosine. So let u be that piece. Du we'll call for a 5 dx. Now when we look, we have cosine of 5x and we have dx. So I have what we need to take care of u. Right? So there's my u. I can take care of that, no problem. But what I'm missing is what I need to have for du. I need to have a 5 there. So that will carry through. So since I'm only missing the number, that's good. We can divide by it on the outside. Cosine 5x and multiply by 5 on the inside. So that now everything is ready to go to change over. All right, we have our u and we have our du. So we can change over to u. Now, part of the reason that I teach it this way as opposed to an alternative way that you might have learned, which is solving for dx here, is because doing it this way, we remember that cosine is the derivative of positive sine. By doing it this way, once you are comfortable with this, you can actually cut out these two middle steps and jump right to the answer 1/5 sine 5x plus a constant. All right, so once you're comfortable, realize this is going to be cosine u, the antiderivative of cosine is sine, then 1/5 sine of 5x. All right, and we're able to make that transition. So cutting down some steps, once you're comfortable with that. If you learned the other way of solving for dx, then that really doesn't lend itself as well to this kind of cutting out steps later on. So that's kind of why I teach it this way, of making sure I match everything up I need for the u and du. And that way, later on, I can cut out these middle two steps and just jump from this result, knowing it's going to be a sine of u, right, and work that problem out that way.